Hello, I welcome you all in this course on mechanical measurement systems. Today we will continue to discuss the step response of second order system. So today we will be discussing second order system step response and we will solve certain examples. So last time we finished at the point where I wrote the omega d or frequency of damped vibration as omega n minus 1 minus zeta square for underdamped system. Now how this is okay, differential equations are okay, but how these systems are going to behave in actual practice. Now in actual practice, if we draw curves using these equations, response curve of different systems, on y-axis we can take k by qis, sorry, not k by q, qo by k qis, right? And on the x-axis, time, temperature, time we can, or omega and t can be taken, because in all the expression, the omega and t are appearing together, right? So we are taking omega and t on x-axis. So for this, qo by kqi is equal to 1. Suppose the line is like this, where qo by kqi is equal to 1. Now we will see the response of, we will start with the response of overdamped system. Overdamped system means when zeta is greater than 1. Now overdamped system will be something like this. The behavior of overdamped system will be something like this, right? Very sluggishly it will respond, and after certain value of omega and t, it will come closer to this, but very sluggishly it will respond. So if you have a second order voltmeter, or I mean this is overdamped, so the moment you give the input, very slowly the needle will move and it will indicate the input to the instrument. And this is, let us say, is curve for zeta is equal to 1.5. Now the second is critically damped. Now the critically damped system will respond to the input, and earlier it will occupy the value of, or it will get the value of qo by kqis, but there will not be any overshoot in the system, in the response of the system. So this is zeta is equal to 1.0. Now critically damped system, not critically, this is underdamped system. In the underdamped system, the system will behave, let us say zeta is equal to 0.6. Now the 0.6 will go like this. If it is, this is, let us say zeta is equal to 0.6. Suppose zeta is, or the damping ratio is 0.2, right? So if it is 0.2, then it can go like this, or 0.1, further overshooting, right? So when the damping ratio is reducing, the oscillations in the response of the system will be developed, and when zeta is equal to 0, there is a situation where zeta is equal to 0. When zeta is equal to 0, there is no damping, the system will continue to oscillate. So we should choose a system. While choosing a system, we have to be careful. Now we have to be careful that we should not go for a system where zeta is equal to 0. At the same time, we should not go for a system which has zeta is equal to 1.5. Even critically damp is not recommended, though it appears to be, from the name itself, the critically damp is the most suitable instrument, but it is not the most suitable instrument because it will also take sufficient time to get settled. The best value of zeta is between 0.6 to 0.8. So it depends upon the, how quick the response of the instrument you want, but here there is only a little overshoot. This is 0.8. So there is a little overshoot and vibrations are not there. So just simply suppose you are giving 220 volt, it will go up to 225 and immediately come back to 220. It is something like this. So this zeta value has to be between 0.6 to 0.8 depending upon the how quick response you want from the instrument. Suppose, so it is not 0.8, it is, let us say 0.4. 0.8 will be below zeta, yes. 0.8 will be below zeta, but there will be a little overshoot in the 0.8 also. So the instrument which we are going for should have zeta between 0.6 to 0.8. This is about, say, okay, above 0.6 it is going to be 0.4, not 0.8. So in that case, suppose I want that the instrument is settled within 10% range, within a 10% range, and that for 10% range settlement, for zeta is equal to 0.6, the settling time is 2.4 by omega n. So if I want to have settlement, if I want to get instrument settled within 5% of error, then the value of zeta has to be in a range of 0.10, 0.7 and 0.8. So normally it is recommended that the value of zeta between 0.6 to 0.8 is fairly good, or if you want quicker response, then one should go for 0.7 to 0.8. Right. And further in this figure, a correction has to be made because this is 0.4, this is not 0.6. Sorry, 0.8. So now, after this, we can have one more step response for omega n is equal to 10. This is one way or generalized way of representing the response of the system. Now, the response of the system you can generate through MATLAB also. So in MATLAB, if you take omega n is equal to 10, right, and then this is Qo by Qi1. This is time t. Now here we are not taking omega t, we are taking only t. And when the damping ratio is 2, the response is like this. That is zeta is equal to 2. When we take zeta is equal to 1, the response is going to be like this. But when zeta is 0.3, in the case of 0.3, the response is, there are going to be the vibrations in the output signals. So there is going to be overshoot. This is known as overshoot, right? And then after a certain time interval, it will get settled in a particular error band, maybe 5% or 10%. Now suppose in a second order system, zeta is equal to 0. Sorry, we'll start with this. Error in measurement, dynamic error in measurement by second order systems. If you want to have dynamic error in the measurement, that is equal to Qi Qi minus Qo by K. That is a error in measurement, and that is going to be equal to, if you look at the equation for underdamped vibrations, then it is going to be e raised to power minus zeta omega nt divided by under root 1 minus zeta square sine 1 minus zeta square omega nt plus phi QIS. So this is the order of error in underdamped instrument which has input of QI and getting QIS output. So if you look at this under a steady state, when T is very high, this is tending to be towards 0. Now response of second order underdamped instrument, underdamped system for zeta is equal to 0. When the zeta is 0, then underdamped instrument gets the response as Qo by KQIS is equal to one minus sine omega t plus pi by 2 when zeta is equal to 0. Okay, and this is going to be equal to nothing but 1 minus cos omega t. Sine omega t plus pi by 2 is cos omega t, and this can be considered as the response of dynamic response of an underdamped system when the value of damping ratio is 0, when this is 0. So the system is going to have constant oscillations, as I showed you earlier also, and the waveform can be determined using this equation. Now, time domain specifications, if you go for the time domain specifications, well, for the instruments, first of all, the first question we ask, how fast the system moves to follow the applied input? Because for any purpose of measurement, this is the first question which is obvious, that how fast the system is responding, whether the system is oscillatory or not, because it may be quick in response with a lower value of this. But if the system output is oscillating, then it is of no use until unless it stabilizes. So there are three things. First is how fast is system, whether system oscillates. If it oscillates, then how much time it takes to get settled. Right? So in order to find this, we will calculate certain parameters, and the first parameter is rise time. Suppose there is underdamped system. In underdamped system, this is Qo by KQi, and system is behaving like this, for example, or amplitude of vibrations is reducing. First thing is rise time. How much time the instrument takes to reach the 100% value? And this rise time, if you look at the equation for underdamped vibrations, that is QO by KQIS is equal to minus e raised to power minus zeta omega nt divided by 1 minus zeta square sine under root 1 minus zeta square, sorry, omega n t plus cos inverse zeta plus 1. That is the equation for underdamped vibrations. So when the 100% value is attained, this becomes 1, right? And when it becomes 1, then this one and this one will be cancelled out. So this expression is going to be equal to 0. And when this expression is going to be equal to 0, then we can say the sine this expression is 0, or we can say that sine of under root 1 minus zeta square omega n t plus cos inverse zeta is equal to 0, because this is 1 and 1 is cancelled out because output is equal to input, and we are remained with this expression. This will naturally become 0. This is not 0, so this has to be 0, right? So this has to be 0 means we have written this expression like this: either it is 0 or this is equal to pi, because sine 0 is 0, sine pi is also 0. So this is equal to pi, and then we can write that this is equal to pi right? Now we can further simplify this to find the TR. This is rise time, and the TR is pi minus cos inverse zeta, pi minus cos inverse zeta divided by omega n 1 minus zeta square. This is the rise time for second order system which is underdamped. Now after this rise time is not enough, because rise time gives us when the system output becomes equal to the input, or 100%, we are reaching 100% input. But in underdamped system there is overshoot also. So there is another term which is known as peak time, TP. So this is rise time, this is peak time, and peak time is expressed as TP is equal to pi by omega n under root 1 minus zeta square. This is the peak time. And there is one more thing which we require to know: what is the amplitude of this overshoot. First overshoot will have higher amplitude than the second one, and it will slowly diminish. Damping will take place. If there is no damping, the system will continue to oscillate. So here damping is taking place, and peak overshoot is expressed as exponential of minus pi zeta divided by under root 1 minus zeta square. Right? I am not going much into the mathematics of this, but these are the final expressions This is rise time, peak time, and overshoot, which are helpful in analyzing the second order step response of second order system. Another one is settling time, means the time required to attain the final value in a certain error band. That is settling time. So if I say, okay, the system vibrates, oscillates, and after a certain time interval, though it oscillates, but it oscillates in certain plus 5% and minus 5%. It oscillates in this range only. So this time is the settling time. When the instrument, the output of the instrument is settled in a particular range. So definitely settling time for plus minus 5% will be more than the settling time of plus minus 10%. Sorry, yes, it is more. Yes, it is less. So if I want settling time 2%, then settling time will be much higher. Now I will take one example. Now a statement of this problem is a pen arrangement of a recorder the pen arrangement of a recorder has mass of 5 grams. So there is a recorder which has a pen of the mass 5 grams. Mass is equal to 5 grams, right? What should be the percentage reduction in mass if it's desired to have 20% increase in natural frequency? If the natural frequency is increased by 20%, how much mass will be reduced? So there are two cases, Wn1, Wn2. So this is Wn and this is 1 point Wn, right? And we have to find how much mass reduction will be there. And in a second order system, Wn is equal to under root K by M. Now with this relation, because this is Wn, so Wn1 is under root K by M1, Wn2 is equal to under root K by M2 is equal to 1.2 Wn1. Now from these two equations, we can always find the value of M2 in comparison to M1. And the answer for this is 30 point. You can do it by yourself. The answer is 30.6%. Another example. A second order system was subjected to a step input and the measurements indicated the system had an overshoot of 10% in a rise time of 0.2 seconds. So there is a second order system and definitely it is undertimed because there is an overshoot. So there is a system response, overshoot of 10%, 1.1, overshoot of 10% in a rise time of 0.2 seconds. Rise time is given and overshoot is given 10%, right? Find the effective damping ratio. We have to find the value of zeta and undamped natural frequency of the system. We have to find the omega n and zeta. Two quantities we have to find. So if we look at the expression for overshoot let us denote by m, is exponential of minus pi zeta divided by under root 1 minus zeta square. And overshoot is 10%, so it is 0.1. So overshoot is 10%, so we can take natural log on both the sides and we can do the final manipulation. So it is minus 2.303 is equal to minus pi zeta divided by under root 1 minus zeta square. So here the unknown is only zeta, and when we calculate the value of zeta, it turns out to be 0.591. Because in overshoot, only this zeta is unknown. And overshoot we have taken 10%, 0.1. And by just putting the value 0.1 here, then we can take natural log both the sides, and then only unknown remains is zeta, and the value of zeta is 0.591. When we have the value of zeta, then rise time. Rise time is pi by damped vibration, WD. D stands for damped vibration. These are damped vibration. Rise time is given. Rise time is 0.2 seconds. Now from here we can find the value of WD, pi by 0.2. Now WD is omega n under root 1 minus zeta square. Zeta is already with us. Now the omega n is coming here from here. The omega n is coming as 19.47 radians per second. Right? Once we have calculated the omega n, you can always find the value of frequency. Now the frequency, natural frequency is omega n divided by 2 pi, and the answer for this is 3.5 hertz or cycles per second. So this is all for today, and from the next class we'll continue with the second order system, and in the subsequent class we will be discussing the ramp response of the second order system. Thank you.